this is General Physics 1. General Physics 1 is basically a subject that more on classical mechanics, of course, formally developed by, started with Galileo and then Isaac Newton, and among others. All right. And then on the last part, I don't know if it will be covered, but I understand the modules that will be developed by our division of Davao City will not reach up to thermodynamics. But based on our most essential learning competencies schedule, the content standards that we are trying to hit is up to thermodynamics. So I hope we would have more energy and time to devote as we learn more in a wonderful world of physics. Everything is physics, right? Everything we experience. In fact, what do we learn here in physics? First, we start with, of course, the very nature of what we are studying here. We are in physics. We are studying the with the with the we deal with the biggest to the smallest things that you can imagine. Okay, from the galaxies to the clusters of stars to the to the minute particles that we have, up to, of course, electrons, uh, muons, and then it's being the quarks, then the elementary particles. When you smash together all the proton and proton, when you try a neutron, when you try to smash them together, of course that requires technology, but if you try to smash them, you would discover that it is still being made up of much more tiny particles, and we call them elementary particles. Now the point is, we're dealing with uh, in physics, we're dealing with big things as well as large things, from super hot material to super cold material, to the fastest moving object to the slowest moving object. That's what we're dealing. We're dealing with the extremes. Anything in between, well, that's just chemistry. And of course, it involves to life. That's biology. So physics is a very fundamental subject. And as I said, we're dealing with extremes. Now, and in dealing with extremes, we need to, of course, describe them. And one way to describe them, to be objective, is through measuring. All right, so when we measure, we deal with units of measurement. All right, so basically, we start with mass. Okay, so of course, we measure what else? Mass, length, and of course, time. So in mass, we use the here in the Philippines, and we are using actually SI. So if SI, we use kilogram, kg, kilogram. All right. So for length, we have meters. I use the symbol M, abbreviation M. And then for time, we have seconds. Now, these are fundamental units of measurement as far as SI unit system is concerned. So when we try to describe things, we usually use, of course, these three fundamental units. There are other measurements that can be measured when we say fundamental or base units. You could also have, say, for example, for electric current, you could have for electric current, you have ampere actually. These are what we're using now is ampere. Another is temperature. These are example of fundamental units, and some other stuff. Right? So those are some fundamental stuff. Others, however, we have some derived derived units. Derived units are a combination of these fundamental units. So derived units, such as for example, we have for derived units we have for let's say for force we use Newton. Newton. Okay, sorry. It's supposed to be red. Supposed to be red. Newton. And Newton is a combination of 1 Newton is equal to 1 kilogram. So kilogram is a fundamental unit. Meters per second per second. So Newton here is basically a derived unit of the fundamental units of kilogram, meter, second per second. Another way of writing this is 1 kilogram meters per second square. Okay. Other books, of course, using the laws of exponents, they write it this way. Um, 1 kilogram meters second raised to -2. But basically, there's just the same. Okay? Okay, so that's for derived units. And there are a lot of other units that you could, derived units that we encounter here in our physics. For example, for pressure, we have pressure. We have, pressure. So we have, of course, we use Pascal. And then other is, for example, for work. Okay. So these are examples of entities that we measure that involves derived units, a combination of fundamental or base units. So organize ang writing ko. For pressure, we have Pascal. Dito na lang, Pascal. 1 Pascal, for example, is equal to 1 Newton here. This is just 1 Newton per square meter. That's for Pascal. So this is a derived, then a fundamental of an M. Okay. For work, we have let's say 1 joule. 1 joule. All right. Are you familiar with the terms that I'm writing here? Pressure, work, force. Force is common, right? Okay, so 1 joule, for example, is that's force. Okay, so that's 1 Newton 1 meter. So those are examples of derived units. All right. Okay, so the next thing we have to deal with is the prefixes. Prefixes, but don't worry, some materials will be posted on our Google Classroom. So if you notice, kasi as I said, we deal with extremes. We measure extremes of very large numbers or very small numbers. But it involves a lot of zeros. So to express that numbers, we use, power of 10, prefixes. For example, for the very large numbers, for example, we use tera. Tera symbol is T. This is not very common among us. But sorry, I have to write na lang 10 to 12. That's the power of tera. Let's have common. Ito common siguro sa hard disk drive, no? Terabyte. Then you have your giga. Giga, capital G for small big numbers. This is a 10 raised to 9. I know you are familiar with this. Mega, that's capital M, and 10 raised to 6. That's a million. Then common, kilo, small letter K, that's 10 raised to 3 or 1,000. On the other hand, for small numbers that require, as well, it's not small numbers, for small measurements that involves lots of zeros, when you write it on a usual way of writing, if you're not going to use scientific notation, of course, we start with centi. Centi for a small c, and this is power 10 raised to negative 2. Then you have milli, small m, and this is 10 raised to negative 3. A micro, for example, you have a micro. Of course, there are symbols. All right, guys. So for micro, you have this symbol, micro, and this is 10 raised to negative 6. This is the opposite of mega. You have, of course, nano. Um, the symbol is n, and then this is raised to 10 raised to negative 9. All right, so these are common. You could have another prefixes for smaller numbers, but let's just limit to that for the meantime. All right, guys. So, okay, so those are common prefixes that we use when we express numbers that are very large and very small. Okay. So let's have some example. Okay. So one way of dealing with measurements is we try to convert them. It's not practical to always use meter. For example, and everyday usual in our ordinary lives, but of course with extraordinary living, with our ordinary lives, when we try to describe, let's say, for example, the length or the dimension of our, or let's say the parameter of our bedroom or of our, bedroom or our house, we could use meter. Meter is okay. But if you're going to describe the diameter of a sun or the diameter of a galaxy, or say, for example, the observable universe, meter will not be very practical as a unit when we try to describe it. I mean, those big entities, no? So we have to use one way to express that is using prefixes or other units. For example, we could use kilometers, but for size ng galaxy, it's not practical. So we could use astronomical unit, AU. We could also use light years. It's the distance traveled by light in a year. So to describe those very long distances, extreme distances, all right? Long distances. Okay, another units that we have to use is also the to describe, like say for example, the diameter of an atom. We could use the prefixes again, and then we could have microns. No, microns. All right, so let's have an example. You have seen your electric bill lately. Attending this class surely increase your electric bills. But of course, that's the downside. But on the good side is usually sa electric bill sa Davao Light, you could see previous reading and present reading. It's the amount of energy that you consume sa inyong balay. So, unit conversion, because as I said, na ay mga instances na it's not practical to use the default or the katong common unit of measurement. Okay, for example, example ni guys, 1, 2, 3, 4, 5, 6 kilowatt hour. Okay. Kilo, kabalo naman mo sa meaning sa kilo, no? Okay. Watts is a unit of power, and this is a derived unit. Hour, of course, is a unit for time, and you know hour is composed of seconds based on I presented kayo na earlier, no? Okay, so here in 1 kilowatt hour, this is equal to 3.6 times 10 raised to 6 joules. So 1 kilowatt hour. Joule, as I said earlier, is a unit of energy. And sa kanang electrical consumption nato sa bahay, we're dealing with energy. So if you're going to use joules sa bahay, can you imagine na ano isusulat sa inyong electric bill. Daghan kayo zero. That's 3.6, then followed by 5 zeros. For just 1 kilowatt hour. Imagine for 1, 2, 3, 4, this is 123,456 kilowatt hours. So, in that case, let's try to convert, okay? Because it's not practical anymore. So, but I just have to demonstrate it to you. Let's have, sige, kilowatt hour and convert that to, let's say, joules. So, here we go. 1, 2, 3, 4, 5, 6 kilowatt hours. And then when we convert, we need to use the conversion factor. This is our conversion factor. That's the relationship between kilowatt hour to joules. So we multiply that with, of course, kilowatt hour sa denominator. So that's 1. And then multiplied with 3.6 times 10 raised to 6 joules. On my end, I am trying to use the GeoGebra calculator there. Let's have 1, 2, 3, 4, 5, 6, multiply 3.6 times 10 raised to 3.6 times 10 raised to 6. Of course, the entire quantity will be divided by, okay, will be divided by 1, of course. I'll just have, sorry if I have to show it to you step by step, but do not mind with the graphs. Just focus on this calculator. Later, we will appreciate the use of the graph facility of GeoGebra. You can install that on your cell phone, by the way. It will be equal to, the point is, the answer would be, bilangin na lang natin. So that's basically, that's 10 raised to 10 joules. Okay? So kilowatt hour cancels out. So what you have is 4.4 times 10 raised to 10 joules. Now, that, as you could see, it's very important that we use scientific notation for extreme values, right? So kung wala yan, can you imagine, it's very not convenient, by the way, to write a lot of numbers. But of course, it's good that we have the idea of the prefixes. So we could express this in this manner. So this would be equal to 44.4 times, gigajoules. Yeah, gigajoule. 4.442 times 10 raised to 11. 1, 2, 3. Thanks for the feedback, Charles. Let's count. 1, 2, 3, 4, 5, 6, 7, 8. I hate this. Again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, thank you, Charles. Lahi ata naka-present sa screen, sir. Hindi po makita ang video for. Ay, sorry, ala, nag-react. Okay, so it's not 4.10 raised to 10. It's 4.4 times 10 to 11 joules. All right? So that's converting, expressing an energy consumption of 1, 2, 3, 4, 5, 6 kilowatt hour. And then we use the unit, the conversion factor that in every 1 kilowatt hour, you have 3.6 times 10 raised to times 10 raised to 6 joules. So to determine kilowatt hours, this value in terms of joules, you would arrive, of course, calculation, and then you would arrive here. It's 4.44. Thank you, Charles, for checking my answer. 4.44 times 10 raised to 11 joules, or 44.4 gigajoules. So again, it's very convenient to use unit of prefixes. Desmos.com. I-try sana kung tunan sa Charles, ilang sa karon kay basi og mabulabo po. I'll try to use, try to study first Desmos.com scientific, Charles. All right, now, kanina we converted a unit from from one unit to another, and then expressing it in such a way that it will be convenient for us using the power of 10. That's scientific notation. Okay. By the way, I will post sa atong sa Google Classroom a video that will show to you the implication of every number ng naga-power sa 10. Okay? From 10 raised to 0 to a certain number to a certain power of 10 that will describe the visible universe, the visible or the observable universe, and then 10 raised to -1 up to any negative numbers na exponent ng 10, and its implications sa sizes ng atong ng mga object that we know. All right. Now let's continue. Here's another example of a unit conversion. This time, let's consider an electron. Okay, an electron. Everybody, I think everybody can imagine electron. I know we only imagine. All right, like me, like you, we've been being taught that an electron is like a tiny solid sphere. It's tiny, point-like. It's very tiny. All right. Now, nobody has seen an electron yet. We can only see its effect, but nobody has directly seen an electron. Nobody yet. All right. Okay, so let's consider an electron inside an electron gun. But the point is, the electron is traveling. Okay, let's have an electron, and then this electron is traveling with an energy. So if it's moving, then it has energy, and we know that it's kinetic energy, right? So suppose you have an electron with an energy of this 8 times 10. Now this is a very, very small number because of this power, -16 joules. So we have an electron traveling inside an electron gun, for example, and then it has an energy of 8 times 10 raised to -6 joules. It's a very small energy. But again, electron is a tiny particle. So it only requires, of course, small energy to move fast. In fact, if we could calculate the velocity of this later, of course, na lang, in our future sessions, electrons move fast, relatively fast than the usual speed that you could observe on a vehicles on a highway with this amount of energy. All right. Now, as you could see, if we use the unit joule to describe this energy, it's very tiny. Let me show you if by default, without using scientific notation. Let's express this number. This is just what? This is equivalent to how many zeros? Can you imagine? Point. And let's count 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 8 joules. Okay, that's that's a ridiculous way of writing that measurement or that the energy of an electron. It's a good thing that we use, of course, scientific notation. But again, this is not. It's not convenient to use joule to express the energy of this electron. Again, there's another unit to describe energy of this kung ingani ka tiny ang particles involved because of incredibly small mass, no? So let's have a unit conversion of, consider you have 1 electron volt. This is the energy of an electron on a 1 volt potential difference. Okay, we will have more of the detail of this in general physics too. But the point is, this is the energy of an electron, and no, it's not the energy. This is a unit that we could use when we try to describe the energy of a small particle, such as the electron. So 1 electron volt is equal to 1.6 times 10 raised to negative 19 joules. Dili mo familiar ani nga number? 1.6 times 10 to negative 19. Tagaan ko og candy ang makasulti. Unsa ni siya nga number? Kini lang kana lang. 1.6 times 10 raised to negative 19. What's this number? Familiar mo ani? Chat, you can chat your answer. 1.6 times 10 raised to negative 19. Wala. I-google pa na nila ba? Basically, that's the number we use to describe the charge of a proton or electron, right? Kayo talaga. Anyway, so the point is, that's the unit conversion factor. So let's try to express this energy now. We have, therefore, 8 times 10 raised to negative 16 joules. And then we multiply that because we're converting, because joules is a very large unit to describe this energy of an electron. So let's, ano nagamit pa man ko ato nga symbol, X bar. Anyway, unit conversion is this 1.6 times 10 raised to negative 19 joule. Okay, so it's 1.6 times 10 raised to negative 19, and then this is 1 electron volt. Okay. So Joule cancels out, and the answer would be, using our calculator, we have 8 times 10 raised to negative 16. Where's my negative 16? Negative 16. Okay. Tapos, multiply. I like GeoGebra kasi because of iyang syntax ba? Ang iyang pagka-plaster sa equation. Times 1 divide 1.6 times 10. Kanang dot, by the way, the dot is times, okay? Times 10 raised to negative 19. Okay, so that's the calculation. So it's 4,999, 4,999.99, balik-balik, and the unit is, of course, electron volt. Now, with that, at least it's a simple number now. It's 499. We don't need to use the scientific notation. Now, so in this case, let me continue. See the convenience of using a paper. Okay. Now, if it's being measured that the energy of the electron is 8 times 10. So again, papasok dito ang concept ng significant figure. This is just one significant number. So we have to express our final answer in such a way that it has one significant figure. From here, the energy of the electron would be equal to, round off, approximately equal to 5,000 electron volt. So that's for a unit conversion ng, for small numbers. Okay. Every time we measure, there's always this uncertainty, something that you could not be certain. For example, if you want to calculate, I hope you can see my video, for example, on the screen, that if you want to calculate for the length of this container box, if we are going to use a ruler, all of us have the tendency to estimate, agree. No, di ba? At the end, how would you know the exact length of this material here? if you are going to use a ruler. Okay, so if we want to measure, for example, the length of the ruler using, here I'm using the centimeter. If you notice, on the edge part, I didn't makita. There's no one. Okay. If you notice, on this part here, we tend to estimate. First eye view, I could say it's around 13.5. Yeah, it's 13.5, 13.6. So there's always this uncertainty. I could always write it this way, like this. Um, First measurement, I could say, okay, it's 13.5. All right, and then I could say, pero dili ko sure mura og um, point, 0.5, 13.5 plus, let's say a point, because the precision is 0.01. Example lang ni guys, 0.1 cm. Okay, on the first glance, because I just estimated it, it's 13.5 plus minus 0.1. It means this is the part where I am not sure. Some will agree, will say, oh, it's not 13.5, it should be 13.6. But of course, I'm not sure also, so somebody will just, okay, I'll write 0.1 cm. So all of this portion here, the plus minus part, is actually, that's your uncertainty. It's always the nature of measurement that you could not be certain. I'm sure that it's lagpas ng 13.5, but it has not reached 14 centimeters. See, this is what I mean when I say we have the tendency to, in a way, it's not inaccurate use of the term, but in a way, in an ordinary term, we tend to estimate the minute part. Okay. Now, precision is the concept of precision. Precision is a result. When can we say that the measurement we do, or I did here on the office, a result is precise when similar measurements are obtained using the same method. If you do the measurement on your own using the same ruler, the same type of ruler, and the same object, and if we have almost similar values that we could get, then we could say that the measurement is precise. Okay, but it doesn't mean that the measurement we did is the correct. Okay, pwede man nga nag-agree ta, pare-pareho tag measurement. What if ato na yung gibuhat ingon ani, example lang natay gibuhat mga ingon ani, wala dahil is putol day atong ruler, nagsugod na dahil sa 2 cm. For example lang guys, our ruler is na actually mali. Ang ruler, the measuring device is, of course, we will have the term error later. Okay, so we could have the same or almost similar measurement or value, but it doesn't mean that it is correct or accurate. However, our measurement can be said as precise because of the similarity of the measurements that we are getting. That's the concept of precision. Okay? Kung gano'n sa makakaingon o dili precise, pagka na-measure nimo ing ani, sa sunod nimong pag-measure na po, lain na po value. For whatever reason or whatever causing that, then if you have a varying measurement, it's not precise measurement. Okay? Okay, so that's for precision. Another concept is accuracy. Okay, accuracy. So first, we have precision. Then you have accuracy. The concept of accuracy is the rates to the quality of our result and the closeness to its true value. When we measure, for example, the length of the carton, this container of an ink, if our measurement is closer to the true value, then we could say that it is an accurate measurement. Okay? Now, the question, no one, na is something wrong with that statement? Ako na lang masulti. When can we say that that is the true value? Who knows the true value? Who knows exactly the length of this carton in container, of this box? Who knows the length? Who exactly knows the length? The manufacturer? I don't think so. They just simply measure it also. As you can see, the true value of a material is something that we have all to agree. Unless, of course, I don't know if you believe in God, but something like that. We could only agree based on the evidence of measurement of the true value of let's say, the true length of the material. Okay, we could only agree. That's why, because of that tendency of we need to agree, there's always this uncertainty on that agreement because we may have different measurements along the way. So that's the idea of accuracy. If we all agree na, okay, we have agreed that it's closer to 13.5 centimeters, then most of, probably the length of that material, the length should be around that value, 13.5 plus minus, ay nga nung nag 13.6, sorry dahil guys, mali na, it's not 13.6, 16, it's 13.6, sorry. Okay. So that we should agree on that. So again, accuracy is our tendency to reach our measurement, to reach closer to the true value that we're aiming. Okay, so how can we, of course, get the accuracy? How could we increase it? If we measure the length multiple times. Okay? And then if we all agree, and let's say, kanus ako to bang measure? Usually, as long as there are two ways kasi, depende sa precision ng imong measuring device. And then, some, in this case, for our level, pwede na 3 times. 3, up to 3 times na measurement to reach the accuracy, because you'll just have to get the average. We will have the details calculations later. Now, another factors that affects precision, both precision and accuracy, are the two errors. Okay? Particularly on the accuracy, one is systematic error. Systematic errors is basically, instead na mag-start ka sa 0, nag-start na din imong measurement at 1. So, of course, you may tend to get values na dikit-dikit. Let's say, you would get 14.5, 14.6. You can say you are precise. The measurement is precise. However, because of the systematic error, then you are not accurate anymore. So, that's for systematic error. For random errors, this is something that we could not avoid. This happens always. Systematic error, by the way, should be minimized or should be eliminated. Okay? This can be avoided. Sa may mga reason nagkakaroon tayo ng systematic error. Measuring device, defective. The measuring person, you, if you measure and then nagtinanga ka, dili nimo wala kagatan sa imong gina-measure. So that's one source of systematic error. So that we're done with systematic errors. Then we have random errors. Okay, random errors is probably fluctuations. Something that we could not we could minimize, but something that it's innate of the material. For example, in this case, if you look at this screen shared, again, these are random errors. These are something that we could not, uh, as I said, nag-estimate ka sa laing part, no? So these are random errors. We could minimize kinibitang part nga nag 13.5, 13.6, you could say 13.7, 13.4. We could minimize, as you could see, kung daghan ta nag-measure, guys, if you measure several times, let's say without using this value, you could say 13.4, na pa yung measure usab 13.5 na sad, another is nag 13.6 na sad, 13.7. As you can see, the fluctuations of the measurement uh, can be reduced if we do a multiple measurements. As I said kanina, we could consider three trials, all right, three repetitions. Okay, so that's for random error. Another way, for another source of random error, for example, lang guys, is I don't know, this is very trivial. Ni saka lang ni taas ang length because of thermal expansion, for example. Ni taas ang length sa object nga mo gina-measure. We can minimize random error if we do multiple measurements, random errors. Okay. So again, that's the difference between precision and accuracy. As I said, you can be precise but not accurate. Precision is a requirement, by the way, for accuracy, but it doesn't mean that when you are precise, you are accurate, because probably there is a systematic error in your measurement. That's why you would have a uniform or similar measurements, but not closer to a true value. So that's why it's very important that you minimize the systematic error. In short, you have to be careful on how to do it exactly. That's another level of discussion. Okay, so precision and accuracy is important when we measure things. Okay? Pwede po ka accurate, pero grabe ka, dili, pwede ba yung ana? Dili mang, okay, pwede. Pwede ka nga, dahil dagko kayo difference ang measurement. No? Ang isa, let's say, nag 12, ang isa, nag 18. When you get the average, you would still have closer to 13.5. In your statistics, I think you have encountered the concept of standard deviation. Ayan. Measurements are accurate, as I said, if the systematic error is small or minimized. Dili ginato siya ma-complete, eliminate. Okay? That's for accuracy. Now, for we can say that our measurement is precise and reliable if the random error is small. Atong pagkakaiba-iba ng measurement nato bitaw. Again, nagkakaiba-iba na yun ay reason. So those are the sources of errors, and that would be another discussion na po. Anyway, let's try to examine the ruler. The ruler can measure, ang iyang capacity kanina is, we have 13.5, and then basically we could use the for analog. This type of measuring device is analog. Ano analog? Kay continuous man din nagamit ng tag gradation. Ano bitaw? Ano na yung mga badlit-badlit? Okay. Mao na itong gradation, no? So for analog. Now for analog measurement, basically the uncertainty is based on the smallest division. Pinakagamay niya nga gradation diha. Then you divide it by 2 or half of it. The last is, the smallest is 0.1 cm, and 0.1 cm is 1 millimeter. So this, ang iyahang kuan ani is, pila may kuan sa half sa 0.1. What is half of 0.1? That would be the uncertainty sa atong measurement kanina. What is the half? Based sa capacity ng atong roller. Again, the uncertainty, obviously on this part now, uncertainty is affected by the measuring device. Ora may kaya sa atong measuring device in terms of centimeter. Okay? So this measuring device would not be appropriate to measure what? The size of a cell, for example. The diameter of a cell, the diameter of an atom. Okay? But for ordinary objects, yeah, this ruler works. This can be fine. Okay, 0.05. Okay, so the uncertainty of our measurement earlier is 13.5 plus 0.05. That's 1/2 of the smallest gradation. Okay, so this is the uncertainty of the measurement of the length of this object earlier. Okay, 13.5 plus minus 0.05 centimeter. Based on this ruler, kini man atong gigamit. Ang iya namang pinakagamay nga makaya is 0.1, and then taking the half, it's 0.05. For digital, what's the smallest number na ma-display sa inyong digital timer? I want you to measure the time. The time it takes for this pen. As you could observe, for this pen, from the moment I release the pen and the moment it makes sounds as it hits the table, would that be fine? Raise your hand if you're fine, and if your cell phone or timer is ready. Okay, let's all together. I want you to type in the chat box the time it takes from dropping the moment I release this pen and then it makes sounds on the table. Are you ready? Ready? Go. I hope you heard the sound. Some of you forget to write something. The unit of measurement. 0.81, 0.96. Okay. I think we all agree that we could all agree that the display is on two significant figures. Now, this is something we apply. We are now applying our knowledge on significant figures. Okay. For digital, because we're using digital now, the reading error, the uncertainty, is the smallest division that your instrument can read. What do you think is the smallest value? For example, let's try to consider the answer given by Aziza. Let me share my screen now. Thank you very much for participating, guys. Time. The time that you measure is equal to, okay, the time that we measure based sa na-measure ni Aziza. By the way, if you notice, all of you have a different measurements. No? We expect that. So you might ask, who is correct? Who among you has a correct measurement? Nobody knows. Only God knows, right? We can only agree on the true value of the time it takes to from dropping to measuring of sound. It depends on our agreement, based of course on logical arguments. No, depende sa accuracy sa ato ang pag-measure. Okay. Now the point is, let's go back to the measurement of let's say Aziza. Let's consider kay Aziza lang ha, 0.87 seconds. Okay. For digital instruments, what's the smallest what's the smallest unit? Can you know? That's the smallest division na kaya. So when we try to write that, ang kaya na inyong measurement is kana siya. If you write that, the accuracy is 0.87 plus minus 0.0, because that's the smallest division na kaya niyang i-measure, yang i-display. So that would be 0.87 plus minus 0.01 seconds. Okay, so that's for digital measurements. Another way, as I said, is to minimize random error. Kasi once lang man nato gibuhat. Another way to minimize random error is to repeat measurements. Alright, so I'll try to use the data that you have submitted, and let's try to use the concept of standard deviation to calculate uncertainty. One standard deviation, sorry. The concept of repeated measurements. We need to repeat because we want to minimize random error. Okay? So one way to minimize random error is to repeat measurements. Let's try to consider the measurements made by Cyril, Merenisa, and Dinah. Okay. Here's the measurement. 0.82 seconds, 0.81 seconds. Yeah, for Merenisa, it's 0.81. And for Dinah, 0.80 seconds. Okay, so we know that the timer has plus minus of time. Kanina, plus minus of 0.01 second. Okay, okay. So here, we could get the standard deviation kasi ang sa ato ang klase, we're supposed to get the variance, but no, hindi na. Let's use, we have two ways actually to calculate, two ways. One is standard deviation, SD, okay? And the other is using range. We could use range. Range, half of the range. Half of the range. Range, half. What's the half? 1/2. Okay. Standard deviation involves, katong sa inyong statistics, SD. I will not use sigma because that sigma means for standard deviation of a population. And I think you know the difference between sample and population. Okay. So this is equal to summation of, yeah, xi minus mean, which is x bar. Then you square it, and then you get the number of repetitions that n minus 1. That's for sample, guys. This is the here in the display is for population. Anyway, yun. So we could either use this or this. Now for our class, wag na natin to gawin. This is much easier. 1/2 of range. Okay? Tsaka na lang ta ito ingato ka meticulous pag daghan na ito number. Okay? But for ordinary calculations here, and this is just an introductory, I want you guys, all of my general physics class students, this approach is, but anyway, we could compare the value later. Okay? Now, let's consider 1/2 of range. What is 1/2 of range? It's simple. Katong sa inyong statistics before. The 1/2 of range is 1/2 of range. It means the highest number minus the lowest number. In this case, sorry. Wala po ko screen. Okay. In this case, 1/2 range. Range is highest, lowest. The highest is 82 seconds, 0.82 seconds, minus the lowest is 0.80, so dapat ako 0.80 seconds. So what's the answer? 1/2 of 0.02. That's 0.01. 0.01. Okay, so we have now this value, 0.01 seconds. All right, so earlier, we know that uh, the measuring device has this uncertainty already. Earlier, you have 0.01 seconds, and then here also, as you could see, a lot consistent, 0.01 seconds. Now, we could report this way based on what we did, all right? I'm not saying that this is the ultimate truth, but based on what we did and of the data that we use, all right? The final uncertainty is just equal to the reading error and in here in the repeated reading. So what we could get, this is equal to final uncertainty, that is, earlier we have 0.01 second, then we have another 0.01 second. So, dapat din na lang. Okay, so our total final uncertainty is 0.02 seconds. Okay, so that's uncertainty. So using your cell phone's timer and your way of measurement is equal to 0.02 second ang uncertainty. The final measurement is this. We get the average of all the measurements. So therefore, the final measurement, okay. It's not final. Time of, let's say, falling of the pen. That includes, of course, again, I have to validate, I have to qualify. That includes, of course, the time it takes for sound to travel, to be picked up by the microphone, the time it takes for the signal to be transmitted to your gadget, and for the time it takes from your gadget to your senses and to be processed by your brain, and you have your feedback, and then you press pause on your phone. That's the entire time of falling of the pen that we're talking here, all right? Okay. Now, the average here, it's just 0.81, right? I hope you all agree with me, it's 0.81 second. So the time it takes for the falling of the pen is just equal to 0.81 second plus minus 0.02 seconds. Okay? That is our measurement. Allow me to demonstrate to you using, of course, Google Sheets na lang, using standard deviation. Google Sheets. So the time it takes is, let's say time, we have 0.82 seconds, 0.81, 0.80, right? So if we want to calculate for the standard deviation, I think this can be, let's write standard deviation. Okay, so the standard deviation is equal to, okay, the standard deviation sample. All right, so the first value that we are going, these are the values that we have to deal with, and that's it. Okay, it's still, of course, 0.01. Yay!